Welcome to BKW Physics. I'm Mr. McConley. And I want to kick off today's lesson. We're actually going to get into Einstein's special theory of relativity, but I want to kick it off going back to radioactivity, which was yesterday's lesson. And what we talked about was radioactivity is a disintegration of the nucleus of an atom and until it gets to a stable configuration. And what I want to focus in on today is that during that process, the mass-energy relationship is conserved. You know that saying, like, energy can't be created or destroyed? That idea is going to be applied to radioactivity in other situations. And it all comes about with Einstein's special theory of relativity. And this is probably the most widely recognized equation in the world, I would guess, but probably one of the least understood equations in the world at the same time. E equals mc squared. It seems really kind of simple compared to some of the physics stuff we've done this year. It basically just says that energy, which of course is in joules, just like it's been, is equal to mass, which of course is in kilograms, just like it's been, times the speed of light squared. And if you forget the speed of light at this point, I feel bad for you, but it's 3e8 meters per second, and you're going to square it and plug it right in there. So that equation just seems like, yeah, okay, easy. The math is easy. But why does it work, and how does it work? That's what we really need to talk about. But before I really get into that, let me just do an example with this idea. So say I were to ask you, how much energy is in one atomic mass unit? So energy in one AMU, atomic mass unit. And just as a reminder, if you're not really super great at this sort of thing, you forgot some stuff from chemistry, an atomic mass unit, when we're talking about that, is usually the mass of a neutron. Okay? So I'm asking you, how much energy is really in one neutron? So I need to go to my handy-dandy reference tables and look up the mass of a neutron. I flip to the front page, and I'm speeding this up so we can get through the video, but if you look on the front page, you will find that the rest mass of a neutron is 1.66 e negative 27 kilograms. It's a small number, very small number, but that's how much a neutron is. So if I apply my equation now, E equals mc squared, I'll just take that number and times it by 3e8 meters per second squared, and I will get a 1.49 e negative 10. And that'll be in joules because it's an energy number. But while I'm at this point, I want to show you one other thing that often happens when we're doing these problems. Because, you know, there's nothing special about that. I came up with a number, great. But a lot of times, as you noticed when we did energy level transitions the other day, we like to see things in electron volts. So, how do you get that into electron volts? Yes. Very good. 1 electron volt is 1.6 e negative 19 joules. So we do a little conversion. Well, when we do that, it actually comes out to be a number of 9.31 E8 electron volts. Okay? And this number is important because it is the energy of one atomic mass unit, so we can use it kind of as a multiplier. If we know we have 3 atomic mass units, we can just multiply it by 3, boom! And it's a real quick way to come up with how much energy something has. But in the reference table, they don't write it that way. They write it as a very awkward and, in my opinion, a little irritating. They write it as 9.31 E2 mega electron volts. That's reference table for you right there. Now, I mean, I guess if you look at it long enough, you can realize in your mind, yeah, mega means E6, E2, okay, I got my E8, so it's the same number, it's just a weird way to write it, okay? I'll let the phone ring because video. So this is how many electron volts are in one atomic mass unit. But the next thing I really want to do here is I want to jump over to an example where we're going to take the element nitrogen and I'm going to show you something really strange about that. So if we start with nitrogen as being 15.7N, and just as a reminder, what do the numbers mean here? Like how many protons and how many neutrons do you have in this situation?
7.
Well, 7 is 7 what? 7 protons, right. And protons are a lot of times indicated by 1/1 hydrogen. So I'll just write that to remind that. So you got 7 protons. And it's a fact, if you look it up, that each of these has a mass of 1.0078 atomic mass units. Atomic mass units, a U. And how many neutrons does it have? 8. 8 neutrons. Okay? Because you take 7, you need 8 more to get to the total of 15. So you got 8 neutrons, and each one of those, when you look it up, is a 1.0087 atomic mass units. Notice those are not the same number. One's 7.8, one's 8.7. Well, let's do a little math here. If there's 7 of those, what's that going to give us? Well, I did it on my calculator ahead of time, and it gives us a 7.0546 atomic mass units. And if there's 8 of these, and I multiply that, I get 8.0696 atomic mass units. Now some of you have already picked up on what I'm getting at here. 7 and change, 8 and change is going to give me a total of 15 and change. What's the total mass that's supposed to be? 15. Not 15 and change. And it's actually 15.1242 atomic mass units. I keep writing a mu when I'm trying to write a U. Alright, so this does not equal what it should be, which actually, if you look it up in a textbook, is not exactly 15 either. It's 15.0001 atomic mass units. But for all intents and purposes, that's pretty much dead on 15. And this is quite a bit. It's a whole tenth over 15. What's going on here? Well, the difference, which you can see is about 0.1241, if you take the difference in the ends there, atomic mass units. This difference is called the mass defect. It's called the mass defect. Now what Einstein said, back to Einstein, that's where we're going here. Einstein said that mass is the same thing as energy. They're not equal. Like this number on this side is not the same number as this number on this side because you got to multiply this side by the speed of light squared. But when you do that, then it will come out equal. So they're equivalent to each other. If you have mass, you have energy. If you have energy, you have mass. Well, if I have a mass difference, a difference in mass, then I must have a difference in energy also, right? And that is called binding energy, which you may have heard before, that term, binding energy. So mass defect, binding energy, are you're really talking about the same thing. One's the mass version, one's the energy version. Well, let me kind of spell it out like this for you. When you have a whole nucleus right here, its mass is 15, just about. When you take and start breaking the nucleus into individual pieces, the process of ripping the nucleus into individual pieces, each one of those pieces ends up being heavier than it used to be. Why? Like, that doesn't make any sense. Because it takes energy to pull them apart. And if it takes energy to pull them apart, you are not only talking about energy, you're talking about mass. So the pulling apart process, or breaking it down into individual pieces, ends up making each of the pieces heavier than it would be if it was there as the whole. This is what Einstein figured out, and this is what this equation talks about. It'll directly play into when we do fusion and fission. Okay? But for today, you just need to realize that they're not going to be equivalent. The mass defect, the binding energy, are the same thing, written two different ways. So for today, physics.